To start this video, please recall what we learned in the last video about the meaning of the absolutely convergent series, conditionally convergent series, and divergent series. Basically, this problem is about considering both series. And of course, they can be the same if all terms are positive, but in general, when you see some negative terms in the original series you consider, of course, they are not the same, and the behavior of the two series may not be the same. You see, it can happen that the original series is convergent and the absolute version of the series is divergent. In that case, we actually call it conditionally convergent. And absolutely convergent basically means both are convergent. And the remaining case is that both are divergent. We just simply call it divergent series. And now in this video, we look at the second test. In the last video, we looked at the test which is called the ratio test. So please look at what I've written down here, the root test. Actually, it is somehow a little bit similar to the ratio test we learned in the last video. But instead of dealing with the ratio, we look at the nth root of the nth term, you see? And then you have to take the limit n goes to infinity. Basically, I would like to check what's happening to this term when n goes to infinity. And after the computation of the limit, if you get that the root is actually less than 1, we call it an absolutely convergent series. And the R is bigger than 1, it is divergent. And when the R is actually 1, that's the bad case here. It means we have no conclusion by the root test. It essentially means the root test fails. In that case, you have to consider both series separately by some earlier test that you have learned. And actually, the purpose of the ratio and the root test are quite similar, as you can see if you have watched the last video. But let's do some examples about the root test here. So for example, please look at the current series. If I'm not just asking you whether it is convergent, actually I would like to ask you whether it is absolutely convergent, conditionally convergent, or divergent. In that case, I think it would be bad if you use the ratio test. It's gonna be difficult. But actually, if you use the root test, you can see that the computation is actually much easier because first, you can look at the absolute value of the whole term here, which means I can drop the sign change term, of course. So it means I'll just write this term without looking at the sign change term, right? And the nth root of it, I think is quite clear. It essentially means the exponent 1 over n for the terms inside here. I'm just copying this term. As you can see, the square, I mean the power n is cancelled with the nth root, right? It's the same as the fact that if you have the square, it is cancelled by the square root. So after cancelling the power, you're actually left with the fraction, right? So now, basically, the root test means you have to take the limit n goes to infinity for the fraction you have based on this term, basically. And because now it is the rational function in terms of n, and when we are taking the limit n goes to infinity, we are allowed to just look at the highest power term. And it simplifies the fraction by a lot because we can also cancel the n squared as the common factor in the top and the bottom. After the cancellation, we are actually left with only 1 over 7, right? And by the root test criterion, because 1 over 7 is less than 1, we understand that this problem actually gives us the answer. It is absolutely convergent, right? And that's the answer to this problem.